Welcome to The Explainer. Today, we're diving into something incredibly cool. We're going on a journey from the absolute lowest levels of computer memory, where literally everything is just electrical signals, ones and zeros, all the way up to building and securing a global web application. It's going to be a fun ride, so let's see how all these pieces snap together. Think about it. We use apps every single day, right? But how exactly does a computer go from processing those raw binary signals, just true and false, on and off, to serving up a fully interactive, secure web app? It feels like magic. But to answer that, to really understand that massive leap, we actually have to start down in the trenches. So, part 1, compiling and computer memory. We're kicking things off with a language called C. Down here, the training wheels are completely off. Your computer doesn't natively speak C, so we have to use a command, usually called make, to pull off this brilliant 4-step magic trick. First up, pre-processing pastes in any extra files we need. Then, compiling translates our human-readable C code into assembly language. Third, assembling converts that into actual machine code, the raw zeros and ones. And finally, linking stitches our code together with pre-written libraries to create a program your computer can actually execute. Now, once your program is actually running, its variables live at specific addresses in your computer's RAM, and C lets you access them directly using something called pointers. The best way to think of a pointer is like a street address written on an envelope. It's not the house itself, it just tells you where the house is located. We use the ampersand symbol to say, hey, give me the address, and the asterisk to disreference it, meaning go to that specific address and give me the actual value inside. Honestly, confusing those two is a classic, incredibly common early mistake, so keep that envelope analogy in your back pocket. Now, what's really interesting here is how this solves a massive problem for us. By default, functions in C pass by value. That means they only receive photocopies of your data. If you hand a function a variable, it just works on the photocopy and leaves your original completely untouched. But what if you actually want the function to modify the original? Well, you pass by reference. You hand the function the pointer. So when the function follows that address, it's directly manipulating the original piece of data. Of course, when you're down in the weeds manually managing memory like this, bugs are absolutely inevitable. So how do we fix them? Enter one of the greatest, most legendary tools in a programmer's arsenal, rubber duck debugging. And no, I'm entirely serious here. You literally place a rubber duck on your desk and you explain your code to it, line by line, out loud. The simple act of vocalizing your logic forces your brain to slow down and actually process what you wrote. I guarantee you, 9 times out of 10, you'll catch the bug yourself before the duck even has a chance to answer. All right, moving on to section 2, algorithms, searching and sorting. So we understand how data is stored, but having data is pretty much useless if we can't efficiently find or manipulate it. We need algorithms. But this brings up a really fascinating fundamental problem. How do we actually measure an algorithm's speed? Think about it. One person might be running their code on a 10-year-old laptop and another on a multi-million-dollar supercomputer. A stopwatch is only going to tell you about the hardware. It tells you absolutely nothing about the underlying mathematics of the algorithm itself. To bridge that gap, computer scientists use something called Big O notation. We don't care about a few milliseconds here or there. We care about what happens when your data scales to millions or billions of items. Big O measures how the number of steps an algorithm takes grows as the input size gets larger. And because we're really only looking at that massive worst-case scale, we just drop the small constants. We don't bother writing O of 2n plus 10, we just write O of n, because what truly matters is the fundamental shape of that growth curve. Let's actually apply this to sorting. Things like selection sort and bubble sort use loops inside of loops to swap data into place. Their worst-case time is O of n squared. Now, for 1 million items, that is 1 trillion steps. It is brutally, painfully slow. But then you have merge sort, which takes this brilliant divide and conquer approach. It splits the array, sorts the halves recursively, and then merges them back together. Its time is O of n log n. So even though it's definitely more complex to write, it mathematically obliterates the other methods at scale. Which brings us to section 3, Python, a higher level. Okay, we've done the hard work in C. We've manually managed our memory, we've suffered through the segmentation faults. Now it's time to upgrade our toolkit. In C, you have that separate compiling step, you have to manually allocate memory, and you have to explicitly declare all your types. Python, on the other hand, is interpreted line by line. Memory is handled automatically for you, and types are dynamic. But here is the secret. Under the hood, the concepts of loops and variables remain exactly the same. All that foundational knowledge you just built still applies. You're just typing a whole lot less. Just look at this incredibly clean syntax. Notice anything missing? There are no semicolons at the end of the lines. There are no curly braces wrapping up your if statements or your loops. In Python, indentation isn't just there to look pretty, it is legally part of the syntax. Use a colon and then you indent the next line. If you miss a line of block of code by even one space, Python will throw an error. It inherently forces your code to be perfectly, beautifully readable. Python also gives us a massive upgrade when it comes to data structures, allowing us to move way past the rigid arrays we had in C. We get lists, which can grow and shrink dynamically as you need them. We get tuples, which are beautifully locked and immutable. Sets, which mathematically guarantee that every element is unique. And perhaps most powerfully, dictionaries. These give us incredibly fast, almost instantaneous lookups by using built-in hash tables to map keys directly to values. All right, on to section 4. Flask and web building. So we have all this great logic, and now it's time to actually put it on the internet. For this, we're going to use a Python web framework called Flask. Think of Flask as the glue. Instead of you having to write boring, repetitive server code just to parse HTTP headers, Flask handles all those back-end tasks automatically. That means you get to focus entirely on the fun part, connecting your Python logic to the HTML, CSS, and JavaScript that your user actually interacts with in the browser. Now, a completely, absolutely crucial part of building for the web is understanding HTTP methods. A GET request is for retrieving data, and its parameters sit right there visibly in the URL. A POST request, however, is for submitting data, and it safely hides that info inside the request body. Think about this for a second. Why should a delete account button absolutely never be a GET request? Well, GET requests can be bookmarked, they can be cached, they can be rerun by accident. You literally never want to accidentally trigger a massive database deletion just because someone refreshed their browser history. And this brilliantly illustrates how we map out our web logic using decorators. See that @app.route syntax sitting directly above the Python function? It simply tells the server, hey, whenever a user visits this specific URL path in their browser, run this exact block of Python code and return the result. It takes the incredibly complex task of routing a massive website and makes it beautifully simple and incredibly logical. Finally, section 5, securing your digital world. Because let's face it, all of our brilliant engineering is completely useless if we just leave the front door wide open. Security starts with encryption. Symmetric encryption is super fast. It uses the exact same key to lock and unlock data, but it's really hard to share that key safely across the internet. Asymmetric encryption fixes that by using a public key to lock and a private key to unlock. The genius of HTTPS is that it uses both. It uses asymmetric encryption first to safely agree on a secret passcode across the world, and then seamlessly switches over to lightning-fast symmetric encryption for the rest of your browsing session. Now, here's a golden rule. A website should literally never know your actual password. Instead, they run it through a hash function. Think of this as a one-way mathematical meat grinder that turns your password into a fixed, irreversible string of characters. And to prevent hackers from just using massive pre-computed cheat sheets to reverse those hashes, we add something called a salt. This is just a bunch of random data mixed in before the hash, which ensures that even if two users have the exact same password, they will look completely different in the database. Unfortunately, attackers know all this, and they have an absolute arsenal of siege tactics designed to bypass our walls. Malware tries to quietly take control of your system. Ransomware maliciously encrypts your files to literally extort you for money. DDoS attacks flood your beautiful new Flask server with a tsunami of fake traffic until it completely collapses. And SQL injection, that manipulates your database queries if you forgot to properly sanitize your user inputs. Because passwords can and still do get compromised, we implement two-factor authentication, or 2FA, as a critical fallback. 2FA requires two entirely different categories of evidence to prove you are who you say you are. It combines something you know, like your hashed password, with something you physically have, like an authenticator app generating temporary codes on your phone. Even if a hacker perfectly steals your password, they are stopped dead in their tracks without that physical device. But here is the final thought I want to leave you with. We can build perfect O(n) log(n) merge sort algorithms. We can properly salt every single hash, and we can strictly require 2FA across the board. Yet the vast majority of real-world breaches don't happen because of some sophisticated technical flaw. They happen through phishing. They happen because an attacker exploited human trust or human urgency to get someone to willingly hand over the keys. So I ask you, is our code the ultimate weakest link, or is it our psychology? All the cybersecurity infrastructure in the world cannot patch human nature. meaning a healthy dose of skepticism remains your absolute greatest firewall. Thank you so much for joining me on this explainer, and keep building.